In this module, I wanted to discuss R-Square, which measures the strength of relationships in regression analysis. R-Square is a proportional reduction in error, or PRE measure, and it poses the question of strength in the same way as lambda, which we used for nominal level variables, or Somers dyx, which we used for ordinal level variables. The question is this: how much better can we predict the dependent variable by knowing the independent variable than by not knowing the independent variable? And the answer is always a number that ranges, a proportion that ranges between 0, which means we can't improve our prediction at all, and 1.0, which means we can completely predict the dependent variable with knowledge of the independent. Now, let's look at this scatter plot once again. This is a scatter plot that appeared as an earlier figure in the chapter. And I have drawn one additional component here. We see y bar is the dashed line. Y bar is the overall mean of turnout in this example, the overall mean of y. In this example, the overall mean of turnout, let's say, I believe is 59.9, or about 60%. We have, and I'm going to use Colorado as an example, this is called yi. Each of the individual observations in terms of state level turnout is represented by a dot or a bubble, and Colorado's up here at just about 70% turnout. So the overall mean of turnout was about 60, and Colorado was a bit over 70% turnout. So there's a distance between y bar, which is the overall mean of y, and y sub I, which is the individual observation for Colorado in this case. Now, if we didn't have knowledge of the independent variable, our best guess would be y bar for each state. So let's say someone asked us to estimate Colorado's turnout in 2012, and we did not have knowledge of the percentage of Colorado residents who have a college education or higher. We would guess the mean of y, or y bar. So we would say, about 60%. And Colorado would represent as about 70%. So we would miss Colorado. We would underguess its turnout by about 10 percentage points. And that's represented by the distance between y bar and yi. Now let's bring the independent variable into play here. Here again was the regression equation that we derived for the relationship between a percent college or higher and turnout in 2012. Estimated turnout for any given state is equal to 43.78. That's the y-intercept, the value of y when x is 0, plus 0.60 times the percent of the residents of the state with a college education or higher. So for every 1 percentage point increase in college or higher, turnout goes up by about 0.6 of a percentage point. So for Colorado, the estimated turnout for Colorado would be, just plug the percentage of college graduates in there, 43.78 plus 0.60 times 35.9. Where did the 35.9 come from? Well, that is the percentage of Colorado residents with a college degree or higher. So we plug this value in, and we get an estimated value for the turnout in Colorado of 65.3. So whereas without knowledge of the independent variable, in this particular case, we guessed about 60, now with the leverage gained by the relationship between the independent and dependent variables, we would guess 65. So we would explain, if you will, the distance between y bar and y hat. So Colorado now, even though it's still sitting up there at about 70, we would account for about 5 percentage points of the difference between Colorado and the overall value of y bar. What's left over, of course, is the distance between yi, the individual value for Colorado, and y hat, our estimate for turnout in Colorado. We can use these components that we illustrate with just one state to generalize for the whole sample that we're working on. There's a value called total sum of squares. Let me go back here really quickly. If we were to take this distance between yi, individual values, and y bar, the overall mean of y. And we were to calculate that distance for all 50 states up here and square that distance for each state and then add all those squared differences up, we would arrive at the total sum of squares. The total sum of squares, or sometimes just abbreviated TSS, is the distance between each individual observation, yi, and the overall mean of y bar. Those distances, squared and summed, it's always an impossibly large number, but it can be viewed as a summary of all the variation in the dependent variable. The total sum of squares plays a role in many statistics, and here's really key. Total sum of squares, again, is an overall measure of all the variation in the dependent variable. Well, let's look at two more components. The first, and more important, is the regression sum of squares. And this refers to the distance between the predicted value of y hat, which in Colorado's case was about 65, a little bit more than 65, and the overall mean of y, which in the case we were looking at was about 60. So again, let me just go up here and we'll return. This distance between y bar and y hat, the estimated value of y, if you calculated this distance for all the states up here, squared that distance, and added all those together, you would arrive at the regression sum of squares. And formally, here's how it's represented. Again, the predicted value of y hat, minus the mean of y, which is now, we're explaining this amount, we're explaining this distance between the mean, this proportion of the distance between the mean and the individual observations in each case. This is called regression sum of squares. But of course, we can see that the relationship's not perfect, and there's distance left over. This is called error sum of squares, or ESS. This is the distance between each individual observation, yi, which again for Colorado is about 70, and the predicted value of y hat, which for Colorado was about 65. So we can decompose the total sum of squares into two components, the regression sum of squares, RSS, and the error sum of squares, the amount left over that we can't explain. We don't know why Colorado is way up there at 70 when we're predicting 65. Formally, the error sum of squares is represented by the difference between the individual values, observations on y for each case, minus a predicted value for each case, squared and summed. Now, you might have guessed where this is going. I mean, R-square is simply a ratio. It is a ratio of the regression sum of squares, how much leverage we're gaining, over the total sum of squares, which of course represents all the variation in the dependent variable. If regression sum of squares is a large component of total sum of squares, that is, if many of the cases are falling very close to the prediction line, and we're explaining a lot of the distance between the mean of the overall mean of y and individual observations of y, then R-square approaches 1.0. If regression sum of squares is a smaller component of total sum of squares, then R-square approaches 0. So if we were just as well off as guessing the mean as using the independent variable as a predictive tool, then R-square will be quite weak. But it always ranges between 0 and 1. Here's how to interpret R-square. We would interpret R-square as the proportion of the variation in the dependent variable, represented by total sum of squares, that is explained by the independent variable, which is represented by regression sum of squares. I like to say it in terms of percentages. We'll see that in a moment. For the example of the college education and turnout, the R-square for this relationship is 0.19 and may be interpreted like this. 0.19, or 19%, of the variation in turnout across states, all the variation in turnout across states, is explained by the percentage of college graduates. The rest, 81% of the variation in turnout across states, must be explained by other variables, because as we know, there are a lot of other variables out there that might also account for turnout.